Okay, I'm going to start, and I'm going to be sort of old school here. Shaun's going to have a bunch of slides prepared. It amazes me, these visuals he puts together that would take me days and days. And so thanks for finding us and having us do this. And I had a couple of references, but we'll give you references at the end. But this started with a paper that I wrote with an undergraduate way back in 2009 on a periodic Pascal's triangle, which I believe you were captured your interest. And when Shaun moved to Valdosta, I shared the paper with him, and through the OEIS, well, we knew nothing about corridors, but or lattice paths, and his background's in algebraic topology and mine's in analysis, but it said a paper in motion, and as that paper was getting done, we realized we had everything in order to use a discrete Fourier transform. And don't let Fourier transform scare you, because if you don't have an analysis background, because it's going to be used more of it as a generating function than anything else. And let's see here, but if I said a Fourier transform, you'd probably think of it as being linear, hopefully invertible. We'll call those algebraic properties. We're going to have a very simple convolution property, and we're also going to use a geometric property that a Fourier transform might have, and that is it preserves angle or inner product. And that's going to be my part, is to exploit that, to get sort of a curiosity about certain lattice paths. Now, I don't know, Shaun, can you come over here? Can you angle that a little bit?
All right, let's see. Is that good? Okay.
So you guys yell at us if you need to see a better, picture. Can you see that? Okay.
Looks good.
Duck my head, and but yell at me if I need to write bigger or something. And we're going to take these vectors indexed by the integers, and we're not going to use a subscript notation, but this x in Shaun's part is going to become a spatial, but that x is discrete. And here we'll let n 0 throughout the natural numbers together with 0. And I'm going to, so when we did this the other day, I went a little bit too slow, so you can see all of Shaun's good stuff. But our big workhorse is going to be this operator that takes one of these vectors index minus infinity to infinity and just drags it to the right. And so we called it a right shift. Now in this presentation, you might want to say up and down more than right, and the inverse we might call a left shift, but that's just sort of how we started the project. And we got n-fold composition for r to the n, and you take a vector and no shifting. Well, that's going to be our identity operator, and I'll probably leave this out, but of course it's invertible by taking this big long train and dragging it to the left, or actually up and down are going to be better than left and right. And also our special vector, which if any of you, so way back when I was doing my PhD, wavelets were the big thing. And so a little bit of signal processing background I have. You might recognize the delta function. And that's just going to be this infinite vector, all zeros except 1. And I probably shouldn't say in the middle. I'm not sure what it means to be in the middle of a vector like this, but that's at position x equals 0. Okay. Now let's get to our main structures here. I'm going to take this lattice N0 cross Z, and you might have to move that in a second, Shaun, back over this way in a second. And we'll call this time or state, and that we'll call position. And again, Shaun's going to make that higher dimensional in a little bit here. And let me just take our delta vector. And start 1 right in the middle. So here's my index, 1 to, well, middle's not a good word, but here's my index, 0, -1, -2, 1, 2, 3, 4. Moving this way, we're pushing our time or state. And we're going to start with a simple type of lattice path and take it to higher dimensions. We might mention a few variations here and there, but let's say the rule is I got to progress in time, and I can go either up or I can go over up or over down. And in a moment here, we might start calling this a corridor path. Once we put walls in, so we're going to put some walls in, and that's the so-called classical corridor path. But right now, let me keep it unrestricted for a second. And if you drew one of these paths, especially if you had some walls in here, you almost see a sine and cosine nature to it is going to form. So Fourier analysis might be a way to approach it. And if I said, so let's say this is time 0, 1, 2, 3, 4. And so we're going to call this state 4, V sub 4, and our index, we'll write it sort of like a function notation, but that x is discrete. So these are going to do our work for us. Now, if I said how many paths get here, that's going to be how we fill in the vectors. So let's see, we're position time 0, 1, 2, 3, 4, position 2. And so that would be V4, 2. How many paths can reach there? And let me do this real quick. And I've actually made some high school contest exams sort of based off of these type of structures. But this one path with our rules can go up or down. So we got a bunch of zeros, a 1 and a 1. Now, how many paths could reach, let's say here? How many paths could reach there? Well, to get there with our rules, we have to start here or here. So each one contributes a path, and we get 2. That would be 1, 1. And in the most natural way, I think you guys see what is forming. So what is forming in a very natural way is our Pascal's triangle. And this entry V4 of 2 would be 4. Other than the indexing, that almost seems the most natural way to get Pascal's triangle. Now, I can encode this simply by using our right operator as follows. To go from one state to the next, I'm going to just shift up and shift down and add. So if I wanted to get this entry here, when I shift up, I'll pick up the 3. When I shift down, I'll pick up the 1. We're using right and left instead of up and down, just to be consistent with our text. Or for our little induction, this, and V0 is our delta right now. And these commute, you could use the binomial theorem and so on. All of our operators are going to commute. Okay. Now for our big example. And let's put some walls in. Let's make a corridor. And I'm going to put a wall in, let's say, down here. And let's go ahead and put a wall up here. I'm sorry. No, Yeah, okay. And I guess both me and Shaun have been, our students think it's amusing. We like to erase with our hands out of excitement. Now, in the classical corridor literature that we've seen, you usually start at 0, but we're going to want to start at 1, and we'll explain why in a second. But let's start with one path here, and the rules is writing up or writing down, but I can't go past that wall, so I can only go up. This can go up or down, and 2. Let's put a few more in. 1 and 3. And Shaun needs to watch me because I often make little arithmetic mistakes. And so this is where our project, began, was starting to look at these things. That didn't directly, but indirectly came up with the picture with the undergrad. And it seems the classical literature is interested in the total number of paths that reach a given state. So I start off with one path at the state 1, n equals 1, one path, state n equals 2, a total of 2 paths. These are called corridor numbers, and at least the literature we read. 3 paths, 5 paths. Anybody want to guess what comes next? Are you hearing me? We're not hearing you.
8.
8, very good. And so another way to get the Fibonacci, now if I lower that top wall or heighten that wall, then that sequence will change. And so we discovered these sequences in the undergrad paper, the OEIS Lattice corridors. Now, the problem is if I want to go from one state to the next, it's not quite as nice. To get a middle number, I could do the up and down, but up here, there's nothing up there. Down here, there's nothing down there. And so, unfortunately, because of our technical difficulties, wish I had a little bit more board space, and I had a little bit more written down earlier. But this is the key thing that we're going to exploit throughout the whole presentation, is these V's that right now my index is from 1 to 4, 1 to 4, 1 to 4, 1 to 4 to stay in the corridor. We're going to extend. Oh, and let me call this the height of the corridor. And so the height is 4, or D is 5. That D is just going to be a convenient way to keep track of that height in a moment. But we're going to extend by anti-symmetry. Hey, Chris. Leonard. I'm not sure we're always getting volume here.
Hi, Chuck. How are you?
Hey, not bad there. Thanks for coming.
Oh, you're welcome.
And so Chris Leonard was my PhD advisor, and we sort of learned this wavelets and signal processing together as grad students. And so I'm going to require anti-symmetry and 2D periodicity. So this vector here, and so we had some technical difficulties. So hopefully we can get the main ideas across. So in the middle, x equals 0. By odd, we have to have zeros. And so that is the bottom wall in our corridor. And okay, odd. So oops, let's see, odd. The 0 is -0. And you watch me, Shaun. Fix me when I make a mistake. And that 0 gets bounced down to -0. But what happens in these boundaries, what must happen, I'm going to wipe out that Fibonacci. is by periodicity, 8 period. So the period is going to be 2D. In this case, 2 times 4, 8. These two numbers have to be the same. By anti-symmetry, they're opposite. And so these necessarily fill up with zeros. And then it keeps repeating forever. And I won't put all of those zeros in everywhere. But now, here is the key. What happens, let me come over here to this guy. Zero. Now I can use this up and down all the way on these infinite vectors. So if I said, find me this number, go up and down, they zero out. In here, well, get what we want. So those annihilate, and they keep annihilating all the way through. And up here, by periodicity, well, 0 and 0, nothing happens, but by periodicity and anti-symmetry, if this is a positive value, that will be negative, and they'll annihilate. And then the corridor progression that we're initially interested in carries all the way through with that nice compact operator, but with a starting point of and you yell at me if I'm getting bad on time there, Shaun. But with a starting value of 1 and -1 with our delta notation. So that's how much you have, and that's the position. So we put a unit of path, and at position 1, negative unit, it's sort of artificial, but what we're initially interested in is right here, and we now have that nice compact operator, and we're all set up, representation for it, and now we're all set up to do Fourier. How are you guys doing so far? Capturing sort of the gist of it? And now, I don't think I need that anymore, and Shaun's going to take that into higher dimensions and other structures, but that's going to be the key to capture that part we're interested in with our nice compact notation and the DFT. So I'm not going to go through the details on the DFT, but let's start with a dimension big N vector, and let's extend it to be n periodic. And then our DFT, again, this is going to be used more as a generating function than anything else. So don't let you really don't need to know much about much analysis at all to get the hang of what's going on. But let me at least write this down. And as I mentioned, we want things like it to be, let's say, pi over n.
2 pi when you're in.
2 pi over n. Let's say x omega. Okay, but it's linear, it's invertible. I don't even need to write the inverse down for what I'm going to do. But if you're familiar, the inverse, basically I change the x's to the omegas and the sign of that guy. And here is our Pope convolution theorem. This is about, I don't need any type of full-blown convolution. I just need to know how the right shift deals with the Fourier transform. And it is, so you watch me there, Shaun. So n omega v omega, and that is, if you're familiar, more familiar with generating functions, it's just like multiplying a series by x and shifting that series along, the coefficients of it along. Okay. And if we put an n here, an integer n there, we get an integer n over there. And Shaun's going to do a little bit more than this, and we got we covered a lot of famous theorems in the literature using this setup, but I want to instead focus on a geometric property of the Fourier transform, and this is just going to be a usual dot product. Our period is probably going to be 2D, at least to study that classic corridor that I just erased. So that's just your usual dot product, W. And that is at least up to a constant multiple. I don't even think I need to know that multiple for what I'm going to do. But the Euclidean structure is preserved by the Fourier transform. And one thing that always gets me is this. Oh, as long as I got this on the board, you can take the Fourier transform over any period and anything else important. Oh, and this is also whatever period we start with, this remains periodic. Okay. How are we?
Lowercase I somewhere. Let me see.
Mm-hmm.
The last line is plus.
And I'm up to about my last
Okay.
bit here. And Shaun has a lot of prepared slides, so he'll be able to go much quicker. But let's do that second example, the Fibonacci example. So it's a sequence of these infinite state vectors, but we're only interested in what we call the fundamental region from x equals 1 to 4. That gave us the Fibonacci. V0, let's call that delta. And we make this all 2D periodic. And then I can say that Vn plus 1 with this setup is given in this nice compact notation. And on the Fourier side, by my quote convolution theorem, and this is not as hard or scary as it might seem if you don't have a background in this. And then Fourier transform of n. And I'm just going to go quick here so Shaun has time, but does anybody recognize that? That is basically your cosine, twice your cosine. And if I do this delta guy, it's Fourier transform, Vn of omega. And so by induction, to make a long story short, and what is the idea of convolution? Is that it changes this moving dot product. Our up plus down is changing it into a pointwise multiplication. So that is one of the true powers of Fourier methods. And I just want to mention real quickly, Shaun might do a little bit more than this, but if you want to look at the growth of these corridors, so like a really big corridor, you might be able to do a type of eigenvalue, eigenvector, or growth rates. It might be easier to learn that growth rate in this form rather than the original form. And so that's part of our text. And now I'm going to do one last thing here. Let's do a three-way corridor this time. So the two-way corridor, we transition by an up and a down, but let's do a three-way transition. And I should have, I had a 2 cosine pi D on the Fourier side, the only difference if I want three-way transitions is on the Fourier side, I get that. Now let's do I want to do a real quick one because I find this a curiosity here. So Shaun, you watch me. So I'm going to have my walls and my paths, but now I can go right up, right over, right down, not crossing a wall. So 1, 1, 0, and these two, and that guy can go up. And let's do a couple more. Shaun, you can, yeah, 4, 5, 3, and 9, 12, 8, and I think I need one more.
Okay, 21.
21.
Oh, 29.
29 and 20. So that's state 0, 1, 2, 3, 4, 5. It doesn't matter whether it's two-way, three-way, higher dimensions for much of what Shaun will set up. But if I just pick any two and do the dot product, the Fourier transform unwinds it. There's probably other methods, but the Fourier transform unwinds it so nicely. What's this dot product? 8 plus 10, 18, 21. 2 plus 3 is 5. It will show up in the fifth one, corresponding to wherever I started. Oh, and by the way, these methods, you can start anywhere. It almost makes the changes are trivial with this approach. But let me go through the proof. Well, I'm not even go through the proof. What time do we got there, Shaun? I got to go. So the proof all boils down to, well, there's a constant, but the constant will go away. And that was that cosine guy I just showed you. Oops, the mth and nth states. And capital V, Fourier side. And we'll get through this in 1 second. Thanks, Shaun. So M and N. This is a sum. Now the key is that this is real. There's a conjugate that I always forget about. And because it was real, whether I'm doing two-way or three-way, it comes over there. The conjugate has no effect, and I can put the powers together. And what I get is, after back transforming, I don't even need to take it back transform. I get that. But this V0 was 0 everywhere in the fundamental part of the corridor, except 1. And so this dot product, I'm doing this times 1, that times 0, that times 0, and I'm done. And so, Shaun, I know you got a lot to say.
Well, okay. Well, thank you, Chuck. I think these are V0s here, but everything works out very nicely on the Fourier side. Now, what I'll be talking about, I'll be generalizing this a little bit toward multi-dimensions, and I'll take these ideas and even be able to transform them in a way to handle some triangular lattices as well. So what I'm going to do, let me pull my slides up, and I think I know how to share the screen. I might know how after about a year of doing this online stuff. I think we all kind of know what we're doing now.
Well, except me and your funny little finger.
Well, I don't know. So can everyone see this first slide?
Yes.
Okay, counting lattice paths. Okay, so I've included just a few things in my initial slides that Chuck has already talked about. I'm going to kind of fly through these first few slides with you. But what we have here is a definition for our corridor numbers, for our corridor structure that we're going to generalize. And so I want to think about the corridor as actually the discrete set of points 1 through h if we're in the one-dimensional case, and that's the case that Chuck talked about. And then we do extend that to n0 cross z, but keep that in mind, that fundamental corridor will come back. We talked about a two-way corridor path. We can begin our corridor paths at any particular point. It doesn't make it any harder in the analysis. The DFT can handle it. So we can generalize to any starting point. Here's just an example in the one-dimensional case. If we decided to start at 2 rather than 1, you could think of this corridor as the fundamental corridor consisting of 3 points, and you ask how many paths are there with only moving ups and downs. Once you get to, let's say, n equals 7, you can ask how many ways could I get there, right? And that is, it has some application outside of lattice paths as well. It has application in terms of graph theory, talking about the number of walks on a path graph. Okay, so again, as Chuck mentioned, we do introduce another variable just to keep the formulas under control. We let d equal h plus 1, extend by anti-symmetry. These are our states, right, our Vn states, and we do extend by anti-symmetry. I'm going to show you a picture on the next slide. We extend by 2D periodicity, okay? And the reason that we do that, again, this was already explained, but we needed to do this so that we can come up with a simple recursive formula that is valid for all input. So we don't have any edge cases to deal with. Now here's a kind of an interesting picture, I think. If you look at the middle of this picture, I know those numbers are incredibly small, so you might not be able to see the numbers, but think about a path that starts at position 1, and you ask, well, how many will go to position 2? Well, there'll be 1 that comes from that. There will be zeros outside of that, right? And then that 1, I like to think about these as propagating to the next state. So the 1 propagates down, propagates up, and now you have this state, 1, 0, 1, 0, where it's blank, it's 0. All right, those two 1s propagate to give you a 2, and the 1 upstairs to give you a 1. And as we all mentioned, we take that structure, think about all those vertex numbers in that corridor, and actually reflect over the x-axis, or the n-axis, if you will, and take that structure, make it 2D periodic. So what we're getting is this infinite back and forth reflection, negation, all the way up and all the way down, and that repeats forever. So the main idea is that you can think of Vn as a periodic function. You can do signal processing on it, which I know nothing about as a pure mathematician. When I heard the word Fourier, that was almost the second worst F word I had ever heard. So when I first heard that, I thought, well, what in the world are we going to do with that? But it wasn't bad. Learning, discrete Fourier transform is not bad, as long as you think of it as a more of a kind of a generating function idea. At least that's how I think about it. So we talked about the left and right shift. I'm just going to very quickly speed through these. And as we talked about, the transition operator is a combination of a left and a right shift. And so we can talk about Vn plus 1, the next state being t applied to Vn. All right. And by induction, of course, that means you apply t to the n to the initial state. Okay, and I say appropriately defined here because we do need that initial state as well to be periodic and antisymmetric. We call that an admissible state. I think that term comes up a little bit later in the slides as well. So the idea, theoretically, we're looking at these transitions that take admissible states to admissible states. And when we have things all properly set up, then we can use the discrete Fourier transform and properties, really nice properties of that transform to do powerful things for us. Of course, we talked about the key property. I'm not going to go through the slides I'm just going to kind of very quickly go through these slides. Of course, this is being recorded, so if you miss something, it's like I tell my students, if you miss something in the slides, it's recorded, go back, watch it later. What percentage actually do? Well, that's a different conversation. We also talked about the initial state, and again, this is valid for any initial position that you want to start at. So the letter A represents an initial position, which we can roll into our V0, okay? And this is on the Fourier side now. We put everything together, and the upshot here is that our main theorem, we can recover the vertex numbers using this fleshed out formula now. And by the way, this formula with sines and cosines, it may look, I don't know, it may look like it has nothing to do with combinatorics, but something like this was already known, even going back to Lagrange, when he was thinking about corridor paths. And so that's kind of interesting to go back in the literature and to see Lagrange has almost a similar formula. So I'm not claiming that what we do here produces new results. It's just a new way of getting some classic results. Okay. Well, the new results, there are some that will come up when we generalize. So how can we generalize these things? Well, we can get three-way paths very easily. We can actually talk about walks in cycle graphs. So the classic corridor can be thought of as counting paths in a path graph. If you want to count paths in a cycle graph, all you have to do is redefine your initial state. Everything else works out the same.
Also, you can think of it as a type of random walk.
Right, and so random walks, yeah, so we can actually talk about random walks. We can talk about taking the limit as the corridor height goes to infinity, unbounded corridors, and all these things actually do generalize to higher dimensions as well. Okay, so with that little bit of introduction out of the way, and please stop me if you have questions, I want to move on to higher dimensional corridor paths. Okay, so my background is in topology and algebraic topology in particular, but so I think for me, I really just enjoy thinking about the visual aspects of things and finding those algebraic structures in in the geometry of the pictures. So we want to think about a corridor now as a r-dimensional box. And so think about all the lattice points that are contained in some finite bounded box. Okay, so the H is going to represent the multi-dimensions of that box, right? Height, length, width, etc. And so the corridor CH, fundamental corridor for this situation, is all of those lattice points in that situation. That's what it looks like in 2 dimensions, right? So 3 by 2. Okay, and so we're going to be able to count paths that start anywhere and progress in time along these horizontal and vertical segments and never leave the box. Okay, and I'll give an example in a moment, but let's continue thinking about the definitions here. A walk in CH can start at any initial point in the fundamental corridor, and the next point is obtained by choosing from a set of valid moves. I'll talk about those moves in a second. You can think about the cardinal directions, but there are other possibilities as well. For our purposes, we're going to have a move vector, which will specify which direction that you want to move in each dimension. Of course, we're going to have to add up a bunch of those to get a good transition operator. I'll talk about that in a moment. Of course, our notation is still the same. V sub n of x is the number of n-length walks, beginning at some fixed chosen a and ending at x. We always fix the a at the beginning of the process. And Vn is called our state function, okay? So then let's talk a little bit about these moves. So a move is a vector where each of these can be 0, 1, or -1. 0 means you don't do anything in that direction, you don't move in that direction. And then the 1 and the -1 are forward and backward in that direction. And of course, we want to talk about shifts, just like we did in the one-dimensional case. An RJ shift simply shifts everything right in the XJ direction. And a transition operator for us is going to be a sum of shift operators from a given move set. So there are going to be, you know, maybe 4 moves, the cardinal directions if we're in 2 dimensions, but maybe we can allow some other diagonal moves and things like that. And so we're going to talk about a sum of these. If you think back to that 2-dimensional walk, 2-dimensional picture, you know, the natural places I can move north, northeast, east, etc. And so these are encoded by these move vectors. And so, for example, southeast is 1 minus 1. And that corresponds to a transition operator of R1, R2 to the minus 1. Okay, so if we want all of our moves to be in cardinal directions, then we encode a transition operator that way with, you know, R1 plus R1 inverse plus R2 plus R2 inverse. We're going to extend our state functions. Remember just how we had to do in 1 dimension, we had to extend our state functions to cover all of Z in order to employ our DFT methods. We're going to do the same here. Everything has to be anti-symmetric in every component independently. So that means, of course, Vn, everything is the same except for this jth component. We can pull out a minus from that. Very much like an algebraic tensor, by the way. So then for j equals 1 through r, we also periodize. So just looking at that one component, periodize in that component. Okay, you can imagine maybe geometrically, what does that mean? We're going to end up tiling the space with these rectangles or rectangular boxes. As a consequence of these 2 items, you actually get zeros in a lot of places. You get them whenever any of the xj's is 0 modulo dj. So again, imagine kind of what that looks like. You don't have to use your imagination. If we look at the next slide, this is what it looks like in that 2-dimensional corridor state. There are going to be zeros everywhere you see white. Basically, those nodes are going to have 0 value. Okay. Now, I think it's kind of interesting also to see if you label these vertex numbers with whatever they happen to be for the situation, just A, B, C, D, E, F. This is an example of one state, perhaps, in the corridor progression. Well, what happens when you do these 2 things of anti-symmetrizing and periodizing? Well, you first flip. Let's say we flip over the x-axis, and you can see now minus D corresponding to D, minus A mirror image with A, okay? And if you flip over the y-axis, now the order looks a little different, but it's still a reflection and a negation. And you can flip again, but now we're going to go back to positive. So, and you can tell if I flip to the left and flip down, that's going to give you the same results if I flip down and flip left. So there are some reflection groups lurking in the background here with some good commutativity properties. All right, once you get 4 of these in 2 dimensions, by the way, that block is going to repeat. And so that's where the 2D periodicity comes in both independent directions. Okay. Again, I'm kind of going fast on this, so if anyone wants to slow me down, let me know.
I'm sorry, can I ask a question? Just for
Go ahead.
clarification. So in the previous slide to this one, you mentioned something about 0. I didn't quite understand that. So you said at some point, if you go to the previous slide.
Okay. Yes,
Yeah.
here.
Here, yes. I didn't understand that part. Could you please explain it? So what does it mean if xj is 0, that Vn will be 0?
Yeah, so if the position, so xj's are components of the position in the lattice. So this could, if we're in 2 dimensions, then because my d is 1 more than h, so that would be 4. So that means positions with x value equal to 0, 4, 8, 12, etc. all are going to vanish in the state. So that means, again, you kind of see these strips of no man's land in between. Okay, if you look vertically, there are 2 in the corridor. We call D h plus 1, so 3, and 0, 3, 6, minus 3, etc. These are all going to be 0. Does that make some more sense?
They're annihilating.
And yeah, so we need those zeros in it for the same reason in the one-dimensional case, that when we progress, that we want to make sure that this A annihilates with something. It's coming in from this minus A and annihilating to give you 0 on the next state. Okay.
I got it. Is there any reason for the color here?
I chose the color so that blue is positive and red is negative.
Got it. Thanks.
All right. All right. So then, so again, the fact that they're supposed to annihilate as you progress to the next state, we need that to maintain throughout all the progression. Therefore, we have to allow transitions that preserve that admissibility. We call it an admissible state if it has that structure. So we need transition operators that preserve that. And I don't have time to go over the definitions, but basically, if a transition commutes with the reflection groups that we're talking about at the time, then we call it a balanced transition, and it's going to preserve admissibility. Again, maybe an example will help out. I'm going to show you an example in a moment. The main theorem, if we do have a balanced transition according to that definition, again, sorry, I don't have the definition on the board of that, but if T is balanced and you have a set of moves corresponding to a set of moves M, and you have an admissible initial state, then the nth state of the corridor is going to be found by doing this process. We take the Fourier transform of the initial state. Here's our convolution property, where it's the transition has a certain formula on the Fourier side that we can simply multiply n times to that result, and then take the inverse Fourier to get back to Vn. And I did hear that there was a ding out there, so that probably means that we have a chat. Well, I didn't see the, oh, numbers look good. Okay. All right. Again, just kind of glossing over a lot of the details because frankly, this is getting into more analysis than I'm comfortable with. But if you look at the definition of the multidimensional Fourier transform, it takes this form when we're in this situation. When I talk about dividing two vectors, it's going to be component-wise, or what I call MATLAB division of vectors. So then this will be a vector and dot product with your move vectors as you sum over that. Anyway, I'd like to get to the pictures, but if there are any questions, I'm happy to slow down on that. Okay. Oh, and this is just another, so this slide just outlines, you know, there are formulas we can find for our initial state. Our initial state V0 is based off of those delta functions that Chuck was talking about, only in multi-dimensions. And then when we go to the Fourier side, they kind of combine in nice ways to give us products of sine functions. The AJs that show up, these are the components of the initial state. In other words, where do we want our paths to begin? Okay, and the DJs can control how big, what are the dimensions of our box. R is the dimension of the box. And so we have very, very good generality there. If we identify only the subset of moves that have non-negative entries, well, we can collect those together and, you know, basically using trigonometry, Euler's formula, both of these things rely on Euler's formula to give us a nice closed form for those things. So again, that's kind of the details, and that's the stuff that, you know, I also like to mention that these things can be taught, maybe not the multidimensional at first, but these can be taught in a standard undergraduate complex analysis course once you get to Fourier series. And so there's a lot of opportunities for undergrad research directions in this. Okay, so that's the fine, that's kind of the nuts and bolts under the hood, but let's see how this actually works in an example. We want to do the number of n-length walks, and let's just do a little bit of work on the whiteboard here real quick, and let's just see what this looks like. So, oops, so then if I guess I better draw this out like so. So what does it mean to progress in a state? Well, here's my 3x2 state, my corridor. This is V0. And if my move set is the cardinal directions, then what I'm calculating here in the next box, okay, I'm gonna ask, well, how do I get to this state? I have to look and see what came in from there, what came in from there, what came in from there. Well, nothing did because there were zeros there. However, if I look at the other boxes on the left and right and above, you can see that this one does progress and contributes to these three boxes, right? And then let's do one more. Hopefully everyone can see this whiteboard that I'm using online. And if not, let me know. But once I get to V2, and let me use a different color here. The 1 and the 1 here are going to contribute and give me a 2. Okay, nothing goes in these checkerboard, the checkerboards, half of them are empty. Okay, what goes down here? Well, there's a 1, a 1, and a 1 coming in to give me 3. And here we've got a 1 and a 1 to give me 2. So yes, you can certainly generate these things the usual way by hand and by adding things up, but our methods are going to allow you to come up with a formula that that simply gives you those things for any n. The formula, as we produce it, and again, I'm just going to kind of really quickly go over this because I know I'm getting close to time, but we have to construct our transition formula. There's our transition on the Fourier side. There's our initial state on the Fourier side, okay? Again, I'm not going to go through where those come from, but if you're interested, I can explain a little better later on if you want to ask questions afterwards. I want to see what this looks like though. So let's do a larger corridor. This has 5 lattice points in the horizontal direction, 6 in the vertical direction. We're going to start at 2, 2, and we're going to allow these non-identity moves. So what does that actually mean? That means that we can go east, north, northeast, as well as every combination where there are negatives instead. So that would cover south, southeast, west, basically the 8 compass directions, all right? And once you find out what the transition operator looks like and what the initial state looks like based off of this initial starting point, then we can calculate and you can program a computer to do this. It's really not difficult, but here's what it looks like. Here's the initial state at 1 at position 2, 2. And so I represented that as kind of a mesh graph where there's a 1 at that point and zeros elsewhere. That's not too interesting. Let's move to the next state. See how that 1 progressed out, and now you have almost like a ring of 1s around it, right? To me, it's starting to look, even at this stage, it looks like you drop a pebble in a bowl of water and watch the ripples kind of go out from there, and they kind of get absorbed by the walls. So anyway, here's what that kind of looks like here, but then let's keep going. Now, remember all 8 of those 1s that were around, and they all progressed in this state to give you a sum of 8 in the middle, and the values are kind of rippling out now. Okay, and as you keep going on, so the numbers get larger and larger, of course, and here it is without the number array, but you can see the profile of what those corridor numbers are looking like. So I'm just kind of going back and forth on those slides. You can make an animation of this if you know what you're doing. I don't know what I'm doing to do that, but at least in the slides I can animate it. So you can also ask about things like asymptotics. You can ask about random walks. Maybe this looks like a probability distribution somehow, a density. You can scale down to a sum of 1 if you want to talk about probability. Anyway, there's just tons of things you can do with these corridor paths. So that's the 2x2 situation, and that would scale up. You could do the same thing for 3 dimensions, 4 dimensions. Of course, the pictures are going to look a lot harder to analyze. So I don't know how to analyze in that dimension, but you can do it. Finally, today I want to talk about walks in these wedge lattices. A wedge, for our purposes, is a plane where it's the plane where you sum the variables and it equals some constant. but we only look in the first orthant of the, well, octant in this case. And so that's a wedge. And what I can do with our methods is we can count paths in this situation. Now, this is not necessarily a new question. In fact, in the literature, there's been quite a lot of work done in these wedge situations. But from what I can understand in our literature search, our method is new in the sense that we can come up with explicit formulas from any vertex to another vertex. The things that are in the literature might talk about the sum, like from an initial vertex, and you progress n states, what would be the sum of those of all those paths. What we do is very stratified. We can actually count from point to another point. All right, so the next picture is very fun. But anyway, what I want to do to use our methods, I'm going to take that triangular lattice and I'm going to embed that guy into Z2. Well, I'm going to embed it into A2, actually. So if you've done any Lie theory or anything, if you know about these algebraic groups, you know some things about the lattice, perhaps. And it's generated by two vectors, alpha and beta. So it's just a module, a Z module in terms of those two generators, alpha, beta. The colors are still representing this idea of a dual corridor structure. Very briefly, the blue here, this right-hand one in the first quadrant, is my lattice that I want to count things in, but I'm going to reflect it and negate it. So reflect, negate, that gives me negative amounts, and then I reflect and negate, and you can go through 6 operations of that around the hexagon. You get back to where you started. Furthermore, I need to take that hexagon and tile the entire plane with it. So that gives us our periodicity. And the idea behind that, why do we want periodicity and anti-symmetry? Well, if we can do things correctly, we can bring it back into the dual corridor idea and use our DFT methods. I know I'm running out of time, but lurking behind the scenes, there's always a reflection group. In this case, a triangle group, which is called delta 333. There are other triangle groups that we can analyze as well. We want our transition to be balanced. In this case, it means it has to be invariant under that reflection group. And so there are really a total, well, there are 3 at a time. This kind of breaks into 2 balanced transitions that if you want all 6 of the directions, you just add them up. All right. And then we call our state admissible. Again, this is just a generalization of the earlier definitions, but we call our state admissible if it has a certain property with respect to elements of our reflection group. Basically, you apply a reflection. It should be the same as either plus or minus the original vertex number. Half of them are going to be negative. We call this the parity, how many reflections, even or odd. And the same theorem that we talked about before, if balanced transitions send admissible states to admissible states, then we get vertex numbers canceling at region boundaries. That's important to contain all of the vertex numbers that we need. And of course, the transition, we need that transition to be linear in order for us to use our methods. When we go to these triangle groups, unfortunately, we need to think about other things as well. We need our transitions to be something called local, meaning I can't just jump from one region to the next. I can't just take a hop from this point and try to go across the boundary to that point with a single transition. That would mess up everything, and so we don't allow that. We only allow transitions to local neighbors, and it actually makes a big difference when you talk about other Lie groups like B2 or C2. And so then finally, let me get to my visual for this wedge in R3. We're going to take our paths at one of the corners, and we're going to allow all 6 of the non-identity moves. So let's see what that looks like. Okay, so there's one path The value of 1 is indicating the number of paths. There's only one path of length 0 starting and ending at that point. And then that progresses. There's 1 and 1 at points that are nearby in the next step. And that progresses. And again, it's very much like a ripple effect as I go through these slides. And you can think about the asymptotics of that picture as well, and talk about random walks on a wedge using our methods. That's all I have for you. Any questions out there?
That's great. So let's thank our speakers.
Oh, we thank you.
Yeah, thank you for inviting us.